Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker. This is chapter 12, part 3, multiple linear regression. Okay, as promised, we are going to do an example using some R code and also practice filling out some ANOVA tables for our full model and our reduced model. We're going to go back to the example of the yearly salary of 67 beginning programmers and analysts by looking at Y being the salary, X1 being the number of employees in the firm's information processing staff, X2 being the profit margin, and X3 being the IP cost. So we want to test whether adding margin, profit margin, and IP cost provides additional predictive value, given that the number of employees is already in the model. We're going to use a significance level of 0.05 for this example. So in this case, we have the full model being y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus epsilon. And our reduced model is y equals beta 0 plus beta 1 x1 plus epsilon. Okay, so I've already done some pre-calculations in R that will give you your R squared value, your sum of squares error, your sum of squares regression, and your sum of squares total. Now, in a previous video, we talked about R squared values tend to increase as the number of variables in your model increase. So let's just double check. The predictors in the model being X1, the R squared value is 0.035. And then once we have X1 and X2, the R squared goes up to 0.29. And if we have X1, X2, and X3, we'd have 0.384. Now, if we added additional variables, this R squared should continue to increase, and it has an upper bound value of 1, right? This gives us the percent of variation in the salary that can be explained by the variables in the model. So the more variables we add, the more we can explain. The sum of squares error also should reduce as the number of variables in the model increases. We see that here. Sum of squares due to regression should increase, right? The sum of squares total, that should stay constant no matter what variables are in the model. Remember, because those are just our observed y's minus our y bars, quantity squared, and neither of those things are changing regardless of the number of variables in our model. So the sum of squares total will stay constant. All right, so for the full model, remember we have 3 predictors in our model. We're estimating 4 coefficients, beta 0, beta 1, beta 2, beta 3. So k plus 1 minus 1 is just k. That gives us a value of 3. Okay, n minus 1, 67 minus 1, that's 66. And these should all add up. So the degrees of freedom for the error should be 63. We double check, 3 plus 63 equals 66. Okay, our sum of squares due to regression of our full model, right? That should be 39.290970. So I'm just going to do some rounding here, 39.29. Okay, our sum of squares error of the full model is 62.98. And our sum of squares total is 102.27. Now we're just going to double check. Do these add up? The sum of squares due to regression, the sum of squares error, and the sum of squares total. That looks pretty good. Okay, the mean square of regression, that's going to be our sum of squares regression divided by the respective degrees of freedom. And our mean squared error should be our sum of squares error divided by the respective degrees of freedom. So the mean square for the full model should be 13.09, 13.09699, right? And then we should get 0.9997. Okay, 9997. So our mean squared error is saying that the typical error that we're seeing is about 1. So to get our F value, we see that the mean square due to regression is actually much higher than the mean square of the typical error. So we get a F value of 13.1005. So we compare this to an F distribution with k degrees of freedom for the numerator and n minus k plus 1 degrees of freedom in the denominator. And we get a value that's very, very small. it's less than 0.001. Okay, so this is doing the overall F test, right? This ANOVA table tells us our number of employees in the firm's information processing staff, the profit margin, and IP costs predictive of salary. If you take all of those three things together, are they predictive of salary? And the answer is yes. Now we can do the same thing for the reduced model. Okay, so degrees of freedom of the reduced model. Well, we have G as 1. And if we have beta 0 and beta 1 that we're predicting, 1 plus 1 is 2, but then we subtract 1 to get the degrees of freedom, we get back to G as 1. All right, the error, in this case, it still has to add up to 66, so this should be 65. I'm going to scroll down just a bit so we can get our previous calculations. Okay, our sum of squares due to regression of the reduced model is 3.66167. And so our mean square in this case is 3.66167. Our sum of squares due to error in this case was 98.61236. And our mean square due to error in this case would then be, let's see, mean squared error of our reduced model is our mean squared error of our reduced model is 1.5653. Okay. Notice that the mean squared error in this case is slightly higher, right? And we're not surprised by this because we've only accounted for one variable. So most likely we're going to have more error in our modeling. And we can calculate an F statistic for our reduced model. We get 2.34. Which is not quite significant at the 0.05 level, right? It's 0.0819. All right. Our sum of squares total is 102.27. So the overall F test here, we're saying, is the number of employees alone predictive of the salary? And we find here that at the 5% level, it's not enough information, right? So what we truly want to ask are, is the profit margin and IP cost additionally predictive of salary, given we already know the number of employees in the firm's processing staff? So in this case, we want to say HO is beta 2 equaling beta 3 equals 0, right? And HA at least one of the beta 2 or beta 3 does not equal 0, right? So our test statistic in this case, right? We can take the sum of squares of regression of the full model minus the sum of squares of regression of the reduced model, divide by K minus G, and then divide all of that by the sum of squares error of the full model over N minus K plus 1. So overall, our test statistic is equal to 17.81945. Now, we gave you a few different formulas for the test statistics, so you can apply either formula, you get the same exact thing, so we're happy about that. All right, in general, if our null hypothesis is true, then we know that the test statistic follows an F distribution where the degrees of freedom 1 are equal to K minus G. In our case, that's 3 minus 1, which equals 2, and our degrees of freedom 2 is equal to N minus K plus 1, and in our case, N minus K plus 1, what does that equal? We'll look at our ANOVA table. That's 63. Okay, looking good so far. Okay, draw a picture of this distribution. So it's going to be skewed right. It's going to peak at 1. We get our critical value. In our case, the critical value is 3.14. right? And our test statistic, right, was 17.82. And we can see that our test statistic is much larger than our critical value, right? Our p-value is calculated, right, by taking the probability. Let's look at this. Let's do PF of our test statistic, 17.81945, where the degrees of freedom 1 is equal to 2, and the degrees of freedom 2 is equal to 63. Let's go into R and calculate that. So using R, we find that our p-value is here, it's a very, very small number, 0.1234567, right? But overall, we could just say since our p-value is less than 0.001, because anytime it's very, very small, we can just use this cutoff of saying less than 0.001. That's less than 0.05, which equals alpha, right? We reject HO. Okay, so this area here was very small. It was less than 0.001. Okay, interpret your decision in context of the problem. All right, well, remember that we're talking about profit margin and IP cost. So profit margin and IP cost provides additional predictive value to predicting the salary, given that we already had the number of employees in the model. So there is additional value to having profit margin and IP cost in addition to having how many employees are at the firm. All right, I hope you learned something today and that you try to do this on your own. But before I stop the video, I almost forgot, is that there's a much easier way to do this. All right, you could calculate a linear regression model with all 3 variables, right? And you could calculate a linear regression model with 2 of the variables, okay? This information will give you your y hat values, your regression model. Y hat equals 25.5378, right? Plus 0.0039 x1 plus 0.0957 x2 plus 0.2163 x3, right? This is your linear regression model. In this case, our R squared value was 0.3842. So 38.42% of the variation in salary can be explained by the number of employees, the margin, the profit margin, and the IP cost. If we want to do the overall F test, it's right here, okay? So our F test statistic, and you can confirm, should be 13.1. We're going to compare that to an F distribution with 3 degrees of freedom for the numerator and 63 degrees of freedom for the denominator. In this case, the p-value, which you can find by doing PF 13.1, degrees of freedom 1 equals 3, degrees of freedom 2 equals 63, lower tail equals false, right? That should equal 0.123456. Okay, that means our p-value is less than 0.001. So overall, these 3 variables are predictive of y. Okay, you could do the same thing for fit 2, right? In this case, y hat is equal to 26.096104 plus 0.0032 x1 plus 0.1569 x2, right? There's only 2 variables in the model, number of employees and profit margin. In this case, our R squared value was 0.2664. 26.64% of the variation in salary can be explained by the number of employees and the profit margin. If we wanted to do the overall F test, our F test statistic would be 12.98. And we compare that to an F distribution where the degrees of freedom 1 was equal to 2, and the degrees of freedom 2 was equal to 64. In this case, the associated p-value would also be very small. It's 0.12345, right? That's less than 0.001. All right, so overall number of employees and profit margin are predictive of salary. In this next model, we just have a single number of employees. So our y hat was equal to 29.084 plus 0.003 x1. And our r squared value is much smaller, 0.0358. So only 3.58% of the variation in salary can be explained by the number of employees. If we look at the overall F test, we get our test statistic of 2.414. We compare that to an F distribution where degrees of freedom 1 are equal to 1, degrees of freedom 2 are equal to 65. In this case, the p-value for the overall F test is going to be 0.1251. All right, your homework for today, and it's not to be turned in, it's just to make sure that you can get it, is to see if you can get all these values from this video and see if you can understand, like, what's the difference between that overall F test and that partial F test? How can I get all of this information? All right, I'll see you next time. Hope you learned something. Keep it up.